Welcome to the Pre-Calculus Notes video for Unit 1, Lesson 4, Trigonometry and Average Rates of Change. Today we will be reviewing the graphs of the 6 trigonometric functions and examining how to calculate the average rate of change for a function. Here you can see the graphs of the 6 trigonometric functions. We will explore these functions and their graphs later in the course. The important aspects of the graphs we're looking at today are the similarities between pairs of graphs and how to determine the period of each of the functions. So you'll notice here that sine and cosine look very similar, one just being a horizontal shift of the other. Tangent and cotangent look very similar, except obviously tangent seems to have an upward movement while cotangent has a downward. And secant and cosecant, again, look very similar. They are just a horizontal shift of each other. So the big thing that we really want to look at is the period. Now we know that trigonometric functions are periodic, meaning they repeat after a set interval. So sometimes you're going to be given a graph and you're going to be asked about the period, you're going to be asked about how often it repeats. And the best way that we can do that is to find a very clearly identifiable point on the function and then look at the next time that that point occurs to be able to figure out how far apart they happen in terms of x. So if we look at the sine function here and I say, all right, well, I'm going to look at the minimum value. So the function moves, it hits a minimum here at negative pi over 2. And then it continues on its way and it hits a minimum value at 3 pi over 2. So if I say that this represents one period, I need to find out how far apart they are. Obviously, the way that I'm going to do that is subtraction and say I want 3 pi over 2, the right x value, minus negative pi over 2, which is the left x value, which gives me 2 pi. Now the same thing can be done for cosine. Again, I'm going to choose the minimum just because the minimum is easily identifiable. So here my left value is negative pi, my right value is positive pi. If I do the subtraction, pi minus negative pi, again I get 2 pi. When I'm looking at the tangent function, I have a couple different options. One thing that I could do is choose the x-intercept. So here is one x-intercept, which is at 0. I chose that one because it's very easy to work with. If I move to the right, the next x-intercept happens at pi. So that's the distance I'm looking for. Pi minus 0 equals pi. Cotangent can work the same way. Notice cotangent does not go through the origin, so that's not going to be an option. But what I can look at are these vertical asymptotes. There is a vertical asymptote at 0. There is a vertical asymptote at pi. So again, pi minus 0 equals pi. So the period of tangent and cotangent is pi. When I look at secant and cosecant, they are very different kinds of graphs. Notice that they do not cross the x-axis at all. There are vertical asymptotes, but they do not necessarily represent a line of repetition. So what I'm going to do is I'm only going to look at this lower part here for the secant function. And I'm going to say this has a lower piece to my function, and that lower piece hits a maximum here at negative pi. Next is an upper piece. I come back to the lower piece, and I find that that happens at positive pi. So I'm looking for the distance between those, pi minus negative pi, and again I'm back to 2 pi. For cosecant, I can do the same thing. So let me pick this maximum here, this maximum here. So I'm looking at 3 pi over 2 minus negative pi over 2, which gives me 2 pi. So these are all the standard trig functions. Obviously, they can be moved up, down, left, or right. They can be stretched in both the horizontal and vertical direction. They can be compressed in some way, but this process doesn't change. These are periodic, they do repeat themselves. So as long as we can find distinctly identifiable points, then I should have no problem finding the period. Now, one thing I do want to warn you about is I have been saying that I want very distinctly identifiable points. If I go up here to cosine, and instead of choosing this minimum, what if I said, okay, hey, I want to choose the x-intercept. Here's an x-intercept at pi over, or negative pi over 2. Here's an x-intercept at pi over 2. I might mistakenly say, oh, well, that's pi units long. But note that at negative pi over 2, my function is increasing. At positive pi over 2, it is decreasing. This is not a repetition. So, just to be very clear about that, we want to choose points that are very clearly identifiable and represent a starting point of a new iteration of the function. Our next topic is average rate of change. When we're talking about average rate of change, we understand it's a very common topic in math classes that range all the way from middle school through calculus. When we talk about average rate of change, we're basically talking about the slope of the line that connects 2 points on a function. Now, to find the average rate of change between any 2 points, we're going to use our standard slope formula, which is y sub 2 minus y sub 1 over x sub 2 minus x sub 1, because this is slope between points. Now, things you want to remember. In the past, you probably described slope as rise over run, which is a very common way that we use in middle school and even through Algebra 1. As I said, the thing that you need to remember is that rise corresponds to y value and run corresponds to x value. The reason I bring this up is one of the most common mistakes that I see when I'm working with students who are finding average rate of change is they will put the x values on the top of the fraction and the y values on the bottom, which will give them the incorrect answer. So we're going to do a few examples of finding the average rate of change. Note that in none of these examples will it say slope. It's just going to say average rate of change, but know that we really mean slope. So find the average rate of change between the points 3, 7, and 6, 15. The very first thing that I want to do is I want to decide which point I'm going to say is point 1 and which point I'm going to say is point 2. Which point you choose to be point 1 really doesn't matter, but what it will do is it will determine which x value I'm talking about when I say x1 and which x value I'm talking about when I say x2. So I'm going to say that 3, 7 is point number 1 and 6, 15 is point number 2. If you had decided that 6, 15 should be point 1, it wouldn't make a difference as long as you put in the pieces appropriately. So we know our formula y2 minus y1 over x2 minus x1. So I start with y value from point 2, which is 15, minus y value from point 1, which is 7, x value from point 2, which is 6, x value from point 1, which is 3. Now, some quick math. 15 minus 7 is 8, 6 minus 3 is 3, and my average rate of change is 8/3. When we look at our second example, what I notice is this time we are looking at a graph, and not all the points are clean. Here we have negative 2, 6, which is fine. Here we have 1.5140. It's fine. It will require a little bit of calculator work to do the subtraction, but it is handled in the exact same way. So I'm going to say this is my point 1, this is my point 2. Generally on a graph, my point 1 is on the left and my point 2 is on the right, just for ease. But like before, it doesn't actually make a difference which one you choose, but this is the common practice. So we're going to say y2 minus y1, x2 minus x1. Y2 is 0 minus y1, which is 6. X2 is 1.514 minus x1, which is negative 2. So 0 minus 6 is negative 6. This other one I'm going to have to use the calculator. 1.514 minus negative 2 gives me 3.514. And there is my average rate of change. Now, something to note. This is a negative divided by a positive, which would be negative. If it has a negative slope, then if I were to connect these two points, what I should see is a line that is decreasing, which I do. On the back, we have a couple more examples. Again, I am given a graph. This has the point -5, -2.969. This is the point 2, 1. I'm going to call this point number 1. Call this point number 2. y2 minus y1, x2 minus x1. I get 1 minus negative 2.969. My x value's 2 minus negative 5, which leaves me with 3.969 over 7, average rate of change. Now, in this last example, what we're going to notice is there are a lot of points on the graph. So just looking at the graph, it may not be clear what it is that you're being asked to do because there are multiple points. But there are directions beneath that say find the average rate of change on the interval. Now, something I want to point out, and I want to be very clear, is that this is an interval. This is not a point. So when I look at this, I know that -4 and 0 are both x values. That means I'm actually dealing with 2 points, -4, which I can come up to the graph, and it's 1.881. 1.881, and 0, which has a value of -2.248. -2.248. So these are the 2 points. So the -4 and the 0 that are in the interval both correspond to my x values. So now I can set this up. Again, I can choose whichever one I want to be point 1 and point 2. I'm just going to put them in order because why not? And I get -2.248 minus 1.881. Those are my two y values. My x value is 0 minus -4. All right, need the calculator for this one. -2.248 minus 1.881. Which gives me -4.129 over +4. So there is my average rate of change. Now I'm going to follow with the rest of these in the same manner. -2.4 means that I'm using -2, -2.961, and for -2.248. Do my setup, -2.248 minus -2.961 over 4 minus -2. I know that this is over 6. 2.248 negative minus 2.961 negative, which gives me 0.713. Again, that's my rate of change. The next one is 0, 2. So I know that I'm doing 0 and -2.248, and the point 2 is 2, 2. So I have 2 minus negative 2.248 over 2 minus 0, which gives me 4.248 over 2. The last one that they asked me for is negative 4 to 4. So I have negative 4, 1.881, and I have 4, negative 2.248. Do my setup, negative 2.248 minus 1.881 over 4 minus negative 4, which gives me 8 in the denominator, and my numerator is 2.248 minus 1.881, negative 4.129. Now, the one thing that I want to caution you on, because it's a mistake that some people make, you'll notice that in many of these instances, I have minus negative. I always write it this way because I want to be very, very clear that this operation is always subtraction. Whether I am subtracting a positive number, which you would see like up here, or subtracting a negative number. Because when we go back to the formula shows subtraction. So be very cautious about the way that you write these because it's very easy to do the incorrect operation. All right. Lastly, down here at the bottom, there is a space for you to summarize your notes. As always, write down things that are important, things you want to remember, or any questions that you want to ask the very next time that you're in class.